tough. I didn't get into the battery stuff, so I think what we'll do is we'll lecture through most of the night, and I want to get you through sort of a quick review of a really quick review of math, which is clearly apparently needed. We'll then get into a very quick review of DC electrical and just sort of up to and including Ohm's law and some of the basic elements of DC electrical. Then I'm going to sort of skip forward to batteries and get us as far through batteries as we can tonight, so that next week when we come in, after take roll, get everything settled, we will go out and start doing charging our lead acid batteries. Okay. All right. So. Show it in here. All right. So math. You guys looking at the results of that assessment I gave. 56 students. Only one of you sort of got close to the one problem on weight and balance, which is a really simple problem on weight and balance. So you guys, stuff isn't sticking as well. Oh look, our district is stealing Microsoft Office. Yeah, that's cool. That'll get them all annoyed. Eventually it'll stop working and they'll start whining at them. So we know you guys don't like math all that much. The truth is, math is probably one of the most powerful languages you could ever. I'm not able to add ink. Okay. Cool. I don't want ink on myself. You know, and I don't mean to say you need to do, be able to solve calculus problems or, you know, engineer a spaceship or something like that. But I will tell you that the real power of math isn't necessarily to be able to solve problems, and we do use it to solve some problems. But the real power of math is it's an analytical way of thinking. It's a way of being really clear about what is factual and what is assumed. It's not that either are better or worse. It's just assumed means one set of rules. Factual means a different set of rules. And math does a pretty good job of keeping it all organized, as well as establishing relationships between the different elements. So being good at it is the exact same kind of thing we do when we're doing any kind of diagnostic work. Okay, you're going to go get a bunch of data. You're going to you need to understand the relationship between the different data. So data would include schematics. Data would include readings off of different meters, etc. So it's the same kind of analytical process. So being good at math and or practicing math sort of exercises that same part of the brain that you use in any kind of diagnostic, any kind of diagnostic troubleshooting. Particularly true in electrical, but it's also true in anything else, whether it's medical diagnostic, fuel metering diagnostic, etc. It's always about sort of a process of working with knowns to derive unknowns in some type of framework that's repeatable and that leads you to an appropriate conclusion. So some of the rules of math, and I'm going to go through this pretty quick. I expect part of the reason it's here, we'll go through it, but part of the reason it's here is because it is online. If you get a little bit lost, go back and say, oh yeah, okay, I can remember that. So it won't let me go forward at all. Oh, we had a full crash. Cool. There we go. All right, so you guys remember, may or may not remember, there's a variety of different numbering systems. The Romans had their own numbering system. That was sort of a bizarre one. Where they went up to, they just kept that in bars until they got up to 3, and then they came up with a V minus a bar to get to 4, and then the V was the 5, and then the V with the bar on the other side was 6, 2 bars, 3 bars, then X for 10, and then the same set of rules for L, which is 50, C, which is 100, 500, 1,000, and on and on and on. So you could then derive, in this case, 1,000 for the 1,000. Here, 1,000 minus 100 for the 9. Here, 100 minus the 10 for the 90, and then the V and the 3 bars for the 8. Similarly, a little bit more simplistic, 2,000 plus 10 plus 6. So as you can see, the number of places is completely inconsistent with the value being provided to you. You could have a very low number with a whole bunch of digits out there, being way more digits than a smaller or than a larger number. The counting system we use, or the numbering system we use, is formally called the Hindu Arabic. There are 10 possible 10 possible values, and then once we get past the 9, we then add another column. Okay, add another row. That's probably the simplest for us because it's what we know. The Chinese counting rods, that's one I found that's pretty intense.
Yeah.
My Lord Almighty. Thank God we don't have to use that. Yeah, that's pretty crazy.
Yeah.
You know, one of the things the Chinese did, though, is they came up with a whole series, in terms of commerce. They came up with a whole series of different weights. They had like duck weight, and a goose weight, and a fox weight, and there were little brass weights of various different sizes, named after and shaped like different animals. And anybody that made some of those or owned some of those was actually considered to be fairly wealthy and fairly affluential because they could do commerce, because they had that mechanism for doing it. The Greeks actually did an interesting trick. One of the things we did much later in studying Greek architecture is we came to realize for many years we thought they never understood the relationship of a diameter to the circumference of a circle, which is called pi. And yet they built these amazing buildings that we would have a hard time replicating today. For example, a number of their buildings where they have all of the columns, when you look at them, particularly from a specific perspective, that point where they intended it to be the most awe-inspiring, you look at it, all of the columns appear perfectly straight, perfectly parallel, everything's perfect. Well, that shouldn't be in the real world. In the real world, straight lines tend to parallax out. So what they did is they cut all of those stone columns to be a little bit tapered so that when you were in that one place, everything looked perfect. And that meant every column was slightly different. Well, one of the things that in studying Greek, the Greek language as well as Greek history, is we never really saw the concept of pi being introduced in any of their math. That's because their measuring system, they actually used a measuring system that was based upon the length around a rod and the length across the rod. So literally the value of pi, which they figured out couldn't be derived, was integrated into their measuring system. It's a clever way of dealing with it. Thank God we don't have to do that. We got calculators that make this big, huge number of pi. And guess what? It's not an actual value. It's an approximation. All right? It's an approximation. All right, so real numbers. Real numbers are any value. Okay, just could be any value, rational, irrational. If it's possible on the possible to be on the number line, then it's a real number. There are a variety of numbers that are considered whole. Whole numbers, natural numbers, integers, all slightly different meanings. Essentially, it means we're not going to take whatever it is and cut it up and share. So you get one whole apple, and you're not going to cut it up. Okay, you're not going to have half an apple. You're not going to have half an apple pie. The whole peach pie is mine. Yeah. All right. So that would be an integer, a whole number, a natural number. Counting number is another way of dealing with that. Much of what we do actually won't necessarily address that. On the other hand, if you're building fences and you don't need to measure to 1/8 of an inch, you can measure to 1 inch and it'll be fine. You can get away with using whole numbers, right? Okay, just make a little block that's 1 inch wide and keep everything 1 inch apart and go for it, you know, and it looks okay. So fractional numbers, there's a couple of different ways you might remember we do it. We either state it as a division problem, 1 divided by 2, and call it a fraction, or we actually do the division problem and display it in decimal form. So 0.5 or like for 1/52, 0.0 blah, 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 right? Now, these are all rational numbers. They can be derived and you can get an exact value for it. There are some irrational numbers that we can conceptualize, but we can never get an actual value for it. We talked about one of them, pi. Doesn't matter what, you take any perfect circle, you take the circumference and divide it by the diameter, and you will end up with a number that's 3.14, blah, 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 and it'll just be, there have been many, many people, including very large computers, that have calculated it out to millions and millions of decimal places and have never gotten to a repetitious pattern. The square root of 2 is another one that's irrational. Also, the square root of -1 is irrational. Okay, what times itself equals -1? Okay, well, -1 times -1 equals, oh wait, it equals +1.
1.
Yeah. So no matter what you do, you can't get there. But if I'm doing math and I have this irrational value in there, I might somewhere else be able to introduce that irrational value and have the two cancel each other out. So the idea of having some irrational numbers. So for example, deriving pi r squared, or the surface area of a circle. When you create the formula that does that, and I won't do it, but one of the irrational values that ends up in there, and it ends up on both sides of the equation, is infinity. What is the value of infinity? It means anything you can imagine. If you go in a straight line in space, wherever you've been, whatever you can imagine, you will eventually get there again. And that's one way of describing it. There's many ways of describing infinity. It's irrational. But if I can work that equation such that infinity here and infinity here cancel each other out, what you get left with is pi r squared. Well, that's kind of cool. We don't really care about all the rest of the process. We've got this cool formula, pi r squared. Let's just figure something out, right? So irrational numbers have value to us for the sake of conceptualizing things, if in fact we can get them out of the equation later on, or approximate them to the degree necessary to do the job, right? So if I'm trying to just draw a circle on the ground, pi is pretty straightforward. 3.14 is all I need, right? Okay. If I'm trying to create a circular orbit to launch something over to Mars, I'm going to need to go 3.411389, take it way, way, way out there, right? I'm going to need a much higher degree of accuracy. So the convenience of pi becomes a little problematic because in some cases we can't completely get it out of the equation. Okay, so because there are 10 operators, 10 values, we call that the base 10 system. We go from 0 up to 9, and then we add a second column. Put a 1 there, and then go back up to 0 to 9. Actually, in truth, the first column has a 0 there. Properly, you could say we're going to go 0, 0, 0, 1, 0, 2. And in truth, you could say there's a whole bunch of zeros there. We just don't write them out because there's no need for it. And then eventually we're going to get to, we'll put a 1 here, then 1, 1, and then we'll put a 2. We'll put a 2 here, 2, 0, and on. Okay. Another one which you guys may have played with in general was the base 8 system. Remember we used that for part numbering in AN hardware? Mm-hmm. Because things were broken down into eighths of an inch. So you got to AN7 and then it went to AN10. There was no AN8, right? Because we were just looking at eighths or the dash number on it. We also used base 8 in computing because the basic element of memory, which we call the byte, had 8 registers. Well, let's use base 8 for that. The other convenient thing for it is, we'll get into I think, the next slide. If you put 2 of those registers together, you have 16 possibilities. So this one is a little bit different. Here we just stop 0 to 7 and stop. There is no 8 or 9. Here we're going to base 16, so we're going to go 0 to 9, and then we're going to have to just add some other symbols. Okay, well, they use the alphabet. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And then if we go any higher, 16, and base 10, we would then go 1, 0, 2, 3, 4, right? Okay? And again, probably aren't going to use that too much you won't use it in this class. You will talk about it some in the digital logic class. We use computer languages pretty extensively. The first one, I guess it is there. I didn't talk about it. The binary one, I actually used to work for a guy, did some work for a guy who worked on the original ENIAC computers. He could code in binary. He could think in binary. Literally just rattle off streams of 1s and 0s and instruct the computer to do stuff. It's like, wow, that was really bizarre. He's a good guy, but so what happens there is you only have 2 possibilities, off and on. Charged or uncharged and charged. So the very basic bit of memory, what it really is we'll take a transistor and a little capacitor. And the transistor will allow the capacitor to be in a state of charge or discharge. That capacitor or other media, okay, will be like your flash drive. It'll either be charged or discharged, which symbolically can then represent a 0 or a 1. And this one goes pretty quick because you got your options are 0, 1. Okay, so 0, 1, then you have to go over a column, and then over a column, and then over a column. Well, once you hit the 8 columns, you've now gotten to what's called a byte. And then a byte, you guys remember megabyte memory, a byte is a basic slot of memory. That produces 256 possible combinations. Okay. One of the things you guys may have heard of ASCII, American symbol code for information interchange, something like that. What it was they went through all 256 of these possibilities and assigned something to it. So I think the first one, 0 was, I forget what it was. 32 is space bar. 33 is capital A. 34 is capital B, capital C, all the way through then lowercase. Comma. So all the different things that you see on your keyboard are assigned an ASCII code. And so when you hit one of those keys on your keyboard, it'll send an 8-bit byte defining in binary what key you pushed of one of those 256 variables. The computer will get some binary value and say, okay, they wanted an A, display an A on the screen. or print an A or whatever you're doing. Okay. Suffice to say, and until you work with this, it's a little confusing. What we really want is base 10. Base 10 is what we work with. Okay, then between all the letters, or between all the numbers, we've got to have operators. These guys, as you remember, define the relationships, right? Mm-hmm. So the relationship between resistance and current, when you're trying to solve for voltage, okay, isn't that the multiplication symbol? Voltage, or excuse me, current times resistance. Okay, but that also defines some element of physics. We can say a coulomb of electrons traveling by a given point in a second will have 1 ohm of resistance in that circuit if 1 volt of current is flowing. Okay, so whether it's a division or multiplication, addition, etc., somewhat defines the operator we're going to use. So if we could say, for example, in physics, let's say force. Okay, if I take force, nothing's really happening. I'm applying a force against the wall. But if I start moving the table and I get some distance to that, now force applied, 20 pounds, at some distance times some distance, 20 pounds times some distance, now gets some work done. Okay, and if I do that in a period of time, that will then be an exertion or you know, a use of, or how do I want to say, I will have exerted power and consumed some amount of energy to exert that power. Okay. Now, in electricity, the most common power production in all electric circuits, and usually it's not desirous, is heat. We lose a fair amount of that work to heat. The wires get hot. It's all good if, in fact, we're trying to make toast, right? Okay, yeah, it's good. We're trying to make heat. But if we're not trying to make toast, then it may not be so good. So, for example, let's say we're trying to make light. Well, an incandescent bulb, we do it by making a whole lot of heat. So that the bulb gets so hot that it starts emitting a bunch of photons. We really don't want to waste that a lot of energy and heat. Hence the invention of light-emitting diodes and a bunch of other strategies which don't generate nearly as much heat, but they do generate the emission of a bunch of photons. Right? So it gets much, much more efficient because the LED doesn't have to consume all that heat. Well, but that's still a multiplication problem, right? Okay, so simple ones, you guys remember them all. We use different, if you put 2 together, oftentimes, this one I always thought was a little confusing. If I put A next to B, it's A times B, it means that. But if I put 2 next to 3, it could be 2 times 3 or 23. If it's in doubt, then you either put a period, not down low, but directly at the same altitude between them, or use the X symbol. Or some of the computer systems now don't like the X symbol. They want you to use the little asterisk symbol to mean multiplication. Division, same thing. There's a funny little thing with 2 dots, or we just use the / key. The equal symbol, it's not an equation without the equal symbol. Okay, for it to be an equation, there has to be an equal symbol. There's also, quite often we could say not exact, close but not exact, in which case we could use the approximate symbol, which is an equal symbol with a little squiggly above it. Okay, so let's say I have pi in the equation.
Not exact.
Okay, truly, if I say pi r squared equals, I can't really say that. I can say pi r squared approximate, because pi is an irrational number. Okay, don't really know. Okay, greater than, less than, we typically aren't going to use that too much. Same thing, oh, there's a nice typo.
There's a typo.
Equal to or greater than.
Well, They're both wrong. The symbol's wrong.
Yeah, they got it the other way.
Yeah, they got their backwards, aren't they?
Yeah.
Yeah, good eye. So the one you might use is the plus or minus
Tolerance.
for tolerance. So you'll see this quite often. They'll say a dimension 2 and 22 thousandths of an inch, plus or minus 10 thousandths. So what they're really saying is that goes from, I forget what I said, 2 and 22 thousandths. So it could be anything from 2 and 12 thousandths all the way up to 2 and 32 thousandths. Okay, they're giving you a range. They sometimes will do it a different way, and this is sort of bizarre. What they'll do is they'll say 2 and 12 thousandths, and then just do the plus, and then they'll say 0.020. What that's doing is saying you go to a range from there all the way up to 0.032. It gets you the same net result, right?
Mm-hmm.
But they just displayed it slightly different. More often what they do is they do it this way, and then they'd have that, and plus or minus 10 thousandths. So, all right, symbology there. Power, which could be a whole bunch of exponents. If we put a little negative there, then we're going the other direction. We're going the inverse of it. So it's really 1 divided by that power, or the root. And then the little thing that comes out of the divisor here, or the root symbol, is called the vinculum. It's the only operator that changes depending on the length of the number. I'm not going to test you on the vinculum. It's a cool sounding word, though.
Is it vinculum the over the numbers that's repeating, or is vinculum with the division bar?
It's the part, no, it's the part that goes across that changes length as the number gets longer.
Oh, okay.
Whether it's square root or the divisor.
Vinculum.
Okay, did you guys remember the please excuse my dear Aunt Sally, sort of left or right?
Yeah.
You got to have some order of operations. This can get a little confusing plugging it into your calculator, because sometimes your calculator doesn't exactly follow those rules. Okay, if it doesn't follow those rules, or it's got a mode like engineering mode or radian mode or some other mode that causes it to follow these rules differently, usually if it has parentheses option, you can encapsulate stuff in parentheses to get it to do it first. Then follow the rest of the rules. Okay, for most of these, we don't get into too much trouble until we get into division and subtraction. These two kind of mess us up, which we'll talk about here. I think you guys remember the number line. So, and again, I'm not going to ever try and throw anything up here. This is just for you to go look at. I don't really care about the names, but we do remember the property with addition. It doesn't matter if I go A plus B or B plus A, the result is the same. Same thing with A times B or B times A. It doesn't work with subtraction and division. Okay? A divided by B is not the same as B divided by A, unless they're the exact same number. Same thing is true. A minus B is not the same as B minus A. All right. The associative property within multiplication and division just says if you end up with a bunch of additions, I could do B plus C plus A or in any way, and it would work. Same thing here. I could say A times B times C, B times A times C, C times B times A. It would work the same. The distributive, I think you remember this one where if you end up with a value that's multiplying a complete component, you can multiply the individual components separately. And that also works if this is a minus symbol. In fact, sometimes that's the easier way to solve it. The identity one is just sort of saying that in multiplication, anything times 1 is itself, and anything that has 0 added to it remains itself. Okay? That would also be true if I subtracted 0 from anything. However, and it would also be true if I divided anything by 1. And in fact, that gets down to the very bottom thing. The inverse relationship, I think this one's fairly easy to see. This is not too big of a deal. This is the one we often forget about. 1 times A, or in either case, A times 1A, or 1A times A equals 1, which is the same thing as saying down here, any number could be a fraction. So if you've got if you've got a value and you're not sort of remembering what to do with it, worked so well, did it? I spoke to it, yeah. If I've got an A times B divided by C, I can divide it by 1 based upon this rule here. I can divide it by 1 and I haven't changed anything, right? Now I can just multiply straight across, can't I? Can I say A, B divided by 1C? And then I don't need the 1 anymore. I can drop it off. That helps you solve that one. And then again, the one issue that we sometimes run into on a calculator is we plug a bunch of stuff in and then end up dividing something by 0. And it usually says error, error, danger, Will Robinson. Yeah, it doesn't work. You can't divide it. How many times does 0 go into apple pie?
Yeah, no, no.
Yeah, I mean, it's not even, there's no way to define it at all. I can multiply something by 0 or divide something into 0. It'll always end, either way, it ends up at 0, right? How many times does pi go into 0? 0 times. All right. So for the purposes of our discussions and homework, don't truncate. Round. Okay, rounding says if A is less than 5, drop it off. Drop that last significant digit off, wherever you're breaking to. So if we're going to 2 decimal places, if A is less than 5, then drop A off. If A is equal to or greater than 5, then this 6 here becomes a 7. And the A is dropped off. And it's standard scientific rounding rules. In truncation, what you do is you just, no matter what it is, you just say, so if it's 12.369, you drop the 9 off. If it's 12.361, you drop the 1 off. Okay, well, that would change the value quite a bit. And that's particularly true. You guys have a tendency to see, 0.0001, 2, 3, 4, 5 as a really small number. And you sort of truncate to here, right? Well, the rest of that is significant if we're talking about microamps throughout the entire problem. So by truncating all of that off, we're going to get to some very different resistances or voltage drops or whatever else. I would, if that was the value like amperage total, I would keep it that number of decimal places through the rest of the problem, right? On the other hand, if it's, amperage total is 1.013198872, and all things considered, when I look at the rest of the problem, maybe I could call this, drop this off here and make that a 2 and just go with that portion of it. Right? You sort of have to make your own call in terms of how much it will affect it. How much by percentage does dropping the 2, 3, 4, 5 off change it? Isn't this value about a quarter of this?
Mm-hmm.
So you're changing the value by 25%. Whereas dropping this off here, it's an infinitesimal amount of the 1, not much of the 0 or the here. Really, the 2 Yeah, it's pretty close to the 2, so it's gonna change that just a little bit. But it's not gonna change the bulk of the value that much at all. Right, so kind of use a little bit of common sense there. When I grade these, if you guys are truncating or rounding really badly, I'll grade them wrong. I get that in each of these problems we do, there's gonna be a little bit of error in there. Part of that's calculated, but the other part of it is, guess what? If you pick up any resistor and measure it, even if it says it's, 1%, and it's really good resistor, there's still gonna be a little bit of variance. Scientific notation, we probably won't use it too much, but it's there. And depending on whether you go less than 1 or more than 1, you can use scientific notation to abbreviate some. Then you remember we have all of the different prefix values. In fact, I think the next page is a whole bunch of them. You must have all values into the same prefix, either none whatsoever, or in milli, or in mega, or whatever. It must all be in the same place, or whatever math you do isn't going to work. It's going to come out wrong. Okay? That's another mistake you guys tend to make quite a bit. Yeah, this was the one. That was pretty cool.
Oh my God. I
didn't know most of these existed, but this one's my favorite. Man, I got a Yoda of electrons, man.
You got a Yoda.
Was it a Yoda or a Yada? I'm not quite sure. But I got a Zeta. Got me a Yoda of electrons and a Zeta of protons.
That's crazy.
Man, they're right here in my pocket. You want to see them? Yeah. In truth, what do we use? We use milli a lot, micro a lot. In capacitors, we'll use nano and pico. Don't use deci or centi too much. Everyone's on deci. Use kilo a whole lot, right? And now, because of computers, mega, giga, tera, quite a bit. I don't know, maybe peta occasionally, but okay. The other thing I did not know is how new some of these were. I never knew that mega and giga have only been around since 1960. And Yodas, man, they've only been around since 1991. Dang. And a zepto and a yocto. Well, let's see. So an atto, isn't an atto about the size of an electron? Didn't we say 10 to the minus 18? 6.24, I think it is, times 10 to the 18th. So 6.24 times an atto. Or if you take it the other direction, that would be an exa. Okay, one column has 6.24 exa electrons times 10 to the 18th, right? Okay. This was one you kind of tend to forget a lot. So decimals are always just a fraction of 10, right? Okay, so you could take any decimal, if you want to convert from a decimal to a fraction, multiply the part after the decimal point times the desired denominator. Okay, so let's say I've got 2.625, right? Take this portion and multiply it by the denominator that you want. So let's say we want eighths. So take 8 times 0.625. What do you get?
5/8.
You get 5. Okay? So then change this to 2 and 5/8. Now, if you do that and you end up with some other, it's not a clean number, then maybe it wasn't a good choice. But let's say I ended up with about 5.5. Well, then maybe the thing to do would pick 16, and then I'd get 11/16, or pretty close to it. And then, of course, if it's close, which way do you wag? Well, what are you trying to do? Let's say I've got a decimal value and I'm trying to figure out what fractional drill to use. Okay, well, what I'm going to do is pick the fractional drill that's a little bit less. Drill that hole, or if I could be a little bit over and it doesn't matter, then I'll just drill it oversized. If it needs to be precise, drill it just a little bit less, then ream it to the appropriate size. Converting the other way, just divide B by C. The division problem, right? You want to convert it a fraction to decimal, just plug it in your calculator and divide it. 1 divided by 2 is going to give you 0.5 in the decimal system. Okay. All right. So substitution or algebraic transposition, you guys saw me do that the other day. Remember when I derived the equation? We had, what did we have? I think we had power and current and resistance values, and we were trying to solve for voltage. I forget which one.
Had power and resistance only.
We had power and resistance only.
200 ohms and end up 2.88 watts.
Yeah. So we took both versions of Ohm's law, both portions of Ohm's law, and then took one component of the other portion and plugged it in there so that we had the R in there. Then we did it following the algebraic rules that we just talked about. Okay, we did a little bit of flip-flopping so that the total value of the equation never changed. But we solved for, I forget what we were solving for, current? Yeah, I think we were solving for current.
Current and volts.
So, again, you guys should be able to do some of these, to do most of these. Really, with the P equals IE and E equals IR, you should be able to derive all other 10 formulas. So if you can't, take it upon yourself to start practicing that. Okay, that's some homework study. That way, when you get to the test, you just do it real quickly. And then you remember the algebraic matrix, which you guys all got to see last week. Yeah, if you do. Again, this is up on that one website, so if you're a little bit lost, go back and look at